So what is this question getting at, right? Why are we even focused on this short ladder length? Well, it has to do with kind of envision different like variations of this ladder, right? We could have the foot of the ladder very far away from the fence, even further than in this image, right? The foot of the ladder could be way out here, and it could reach the house at a very low angle, right? But in that case, do you see that the ladder would be very long, right? An alternative to that would be to put it very close to the house, right? So that it's even closer than this. But in order to reach the house, again, that ladder would have to be very, very long in order to make that, to close that distance. So somewhere between kind of this ridiculously close and ridiculously far away, um, you know, boundaries to this, there's got to be a middle value that's much more of an ideal ladder length, that minimizes it instead of having these really long ladders that are either super far away or super close and also very, very steep at the same time. So in this context, the objective function we want to look at is this length of the ladder, right? That's what we're trying to do, the shortest ladder length. Okay, so this is a big focus for us. So how do we represent that? Okay, well, one way to kind of approach this is to use kind of a right triangle. So I'm actually going to draw it out. And it's really going to be looking at this portion of the house right here, using more of a kind of from the side. So it would be as if you were standing right here. How would you look on it this way? Okay, so let's look at that. So you would have the house. Then you're going to have the ground down here. We're going to have the ladder. So this is representing the ladder. And then we're also going to have partway through here the fence. So do you kind of see how that's like a cross section almost of what we're looking at? So this is a right angle, right? The side of the house, and then also the fence should be sitting here at a right angle. According to the picture, and I can erase some of my scribbles if that's helpful. According to the picture, though, we do have some values that we can plug in. So, for example, this distance from the house to the base of the fence is 3 feet. We also know the height of the fence, that's also 8. And then what we're really interested in, or one thing that's really helpful to us, is what is this distance right here? From here down to the ground, let's call that y. And then I'm going to call the distance from the fence to the base of the ladder here, and I'm going to call this distance for the ladder, or the length of the ladder, L. We want to try to express L as a function of X. Okay, so is that possible? Well, I think so. We have some right triangles here, right? So couldn't we represent L squared, that's kind of the larger of our right triangles. I'll kind of outline that for us. This right triangle, L squared, let me use, that's our hypotenuse, is equal to y squared plus x plus 3 squared. Well, that seems to work, right? We can use similar triangles though, right? I don't know if you remember similar triangles from like a geometry, maybe a trig class, probably geometry, but similar triangles give us the relationship y over x plus 3, that's this back where y is over this base where x and 3 are, is equal to the ratio of this smaller, let me outline the smaller right triangle here, that's here. Okay, so that's equal to 8, so it lines up with y. Both of them are those heights. And you can actually solve this for this value of y, right? So we can say y is equal to 8x plus 3 all over x. And that gives us a constraint that we can plug in. So this up here is going to be our objective function, and this is going to be a constraint. Back to this Pythagorean theorem, we have L squared. Again, I'm trying to incorporate this full length of this ladder equal to, and instead of y squared, I'm going to use this 8x plus 3 over x quantity squared plus x plus 3 squared. Cleanup that we can do, I'm just going to write this for a second as L squared, 8 squared, x plus 3 squared over x squared. I just multiplied this squared into each of the groups, plus x plus 3 quantity squared. So just to kind of point out, I have a common factor, and I've used this a couple times. It's kind of like factoring, right? I have this common factor of x plus 3 squared in both of those terms, right? So I could actually rewrite this as L squared. If I factor out that x plus 3 quantity squared, I'm left with 8 squared over x. So we've got L squared is x plus 3 quantity squared, 64 over x squared plus 1. Okay, so we want to start thinking about what are those critical points. So you might pause for a moment and think that this is kind of weird, right? How do we move forward finding a critical number with that L squared there? Normally what we would do is we would solve for L, write this in green, we would solve for L, then find L prime or dl dx, right? Or dl dx. Well, I want to point out, so note, L is non-negative. This means that L is greater than or equal to 0. Okay, so because this is non-negative, L and L squared have local extrema at the same points. So instead of working with L is this giant square root of x plus 3 squared and 64 over x squared plus 1, we can actually just work with L, or take the derivative of x plus 3 squared, 64 over x squared plus 1. And we can just find the derivative of this. And this only happens because we have a non-negative function. So what we can do, I guess I should still call this L squared, but what we can do is we can actually just find the local extrema of this function instead of having to do it with this function. Okay, and again, it's only because we're non-negative and they're going to end up having the same points. So one way we can write this, because the notation gets kind of weird, is d dx of x plus 3 squared, 64 over x squared plus 1. And then what's its derivative? Well, we've got a lot of rules to apply here, right? So first we have product rule. So let me make a note of that. Product. Right? So product rule has us say 2 times x plus 3 to the 1. Chain rule says times 1, right? Times, that's 64 over x squared plus 1, plus the other function, so that's 64, this is 64x to the negative 2, so plus negative 128 over x cubed, and then we don't have anything with that 1 there, times our other function, which is x plus 3 squared. That was the first part, right? So lots of cleanup here. we've got 2x plus 3, and actually we can factor out, which I'll do that in a minute. We've got 64 over x squared plus 1 plus negative 128 x plus 3 squared over x cubed. I do see a common factor. There's a x plus 3 and also a 2 that we can factor out. So 2x plus 3, which leaves us with 64 over x squared plus 1, minus 64 over x cubed times x plus 3. Okay, if I keep just factoring that, we've got 2x plus 3, we've got 64 over x squared plus 1 minus 64x plus 192 all over x cubed. I'm going to get a common denominator, and again, the goal here is that allows us to clean it up a lot nicer. So we've got 2x plus 3. Common denominator, I would need to say times x, and over 1 times x cubed. So we've got 64x plus x cubed minus, and this negative is going to affect this as a group, so minus 64x minus 190 all over x cubed. So notice that these are going to cancel, and we're going to be left with 2x plus 3 times x cubed minus 192 over x cubed. And no, you cannot cancel those two. Okay, so we are setting these all equal to 0. So over here, we get 2x plus 3 is 0, which means x plus 3 is 0. But this gives us x is negative 3. This is outside of the feasible domain, right? So that's not going to work because that's a negative value, right? If you remember what x represents all the way at the beginning of our question, way up here. Right? This is the value of x. There's no way that could be a negative 3. It wouldn't even make sense, right? So there was one set of it. The other set is going to be setting minus 192 over x cubed equal to 0. So numerator x cubed minus 192 is 0. We get x cubed is 192, which when we cube root that, we get x is approximately 5.77, okay? The only other option is if you set where it does not exist, which again is not really aligning with that feasible domain, right? We need x to exist. We need this to work out, right? And also x being 0 would not make sense either, right? So we're going to dump this one as well. Again, we're running into that feasible domain kind of an issue. So we're over here, because we cube rooted, there's no need for plus or minus or anything like that. We would want to check this, scoot over please, using either the first or the second derivative test. The second derivative test is possible, although maybe not the most fun. You could do it. I might actually try the first derivative test here. Why not? First derivative test. So we just need to look at what the function is doing just to the left and just to the right of this. So if we picked a test point, let's say x is equal to 5 and x is equal to 6. So if we take f prime of each of those values, f prime of 5, again, I'm looking up here at this as a fraction, right? So that would be 2 times 8, right? And then this would be 125 minus 192 over 125. And I'm interested in signs alone, which means that this is negative, which means we are decreasing, right? If we plugged in 6, this would be 2 times 9, and 6 to the third power is 216 minus 192 over 216, which means f prime of 6 is a positive value, and we're increasing. So by that first derivative test, because we're going from decreasing to increasing, that makes this point a local minimum. Okay, so let's summarize. So this x is equal to 5.77. This is feet, right? So we would say x is 5.77 feet, is the distance from that fence, right? Gave us a local minimum. Local minimum. So I'm going to go back up to my original question. Because again, you want to make sure you're answering whatever the question asked you to do. So if we're looking at this picture, right, this pink and blue picture that I drew over here, we found this value to be 5.77 approximately, right? So is it possible for us to find the value of L? I think it is. And I think I'm going to use this L squared before we took its derivative. So from here, if x is 5.77, we get L squared, 5.77 plus 3 quantity squared, 64 over 5.77 squared plus 1. If we throw it all on a calculator, we get L squared is approximately 224.77. Square rooting both sides, we get L is approximately 15 feet. And again, we know this is a minimum because of that first derivative test that we applied. Final answer.